Hi everyone. Okay, so here we are, chapter 12. This is the very last chapter of the semester, and it is on the behavior of gases. So to help us understand the behavior of gases, let's recall the kinetic theory that we learned in chapter 10. So according to the kinetic theory, we know that the gas particles are small hard spheres. They have insignificant volume, mostly empty space, no attractive or repulsive forces. And also, according to the theory, we know that these gas particles are in constant and rapid random motion, and the collisions are perfectly elastic. Okay? Also, remember there are two things wrong with the theory: the insignificant volume and the no attractive or repulsive forces. So remember, just put a little star next to those. Those are the two things that are actually incorrect about the theory, and we will talk more about that later. So as we are talking about all these different variables with the gas, we're mostly going to discuss in this chapter pressure, temperature, and volume. Okay, pressure, temperature, and volume. And so these are the SI units, the International System of Units, for these variables. So for pressure, it is the kilopascal, temperature in Kelvin, and volume in liters. So this is something that you should be familiar with. So let's start by talking about this picture here. So let's talk about the top part, what's happening. Let me describe to you what this apparatus is. This is a cylinder, and inside the cylinder, these are the particles inside the cylinder. And you can see that it is attached to a bicycle pump, and then this is a pressure gauge to measure the pressure in the container. So notice the handle is moving up and down. We're adding in more particles into the cylinder. And the more particles we add, the more pressure we are adding to the cylinder, to the point where if we add too much, therefore it could cause this cylinder to burst. Now let's take a look at the bottom picture. Once again, we still have a cylinder. Okay, we still have a cylinder, and it is still attached to a pressure gauge. But notice this time, there is a valve here. So this valve, we can open and close the valve, all right? And then that will allow particles to leave the cylinder. So you can see what's happening here. We open the valve, see the particles are leaving, therefore the particle number decreases. So if the particle number decreases in the cylinder, then the pressure goes down, okay? So fewer particles, fewer collisions, which will lead to less pressure. So the number of particles is related to the number of collisions that can be made, which will therefore affect the pressure. Based on what we just discussed, you should read this and fill in the blanks with the words here at the bottom. So here's your word bank. And so you should pause the video, see if you can fill this in correctly yourself, and then play the video to check your answers. As the number of gas particles increases, the number of collisions increase. Therefore, the pressure increases. If you double the number of particles, double the pressure. Hopefully you got all of those correct. All right, so let's go on to the next slide. All right, so now we're going to go on to Boyles Law. So Boyles Law is a pressure and volume relationship. So if you remember going over the investigation worksheet the other day, this is pertaining to part A of the investigation worksheet. So here we have a cylinder, and in this cylinder it has a piston. That's what this handle thing is called, a piston. So we can pull the piston out, or we can also push the piston in. And so that's going to change the volume of the container. It's kind of like the push pops. If you ever had a push pop when you were a little kid, it's like that. All right, so this is what we're starting out with. Now notice what's happening. They pull the piston out, increasing the size of the container. So the volume here, you can see, is getting larger. So if the volume's getting larger, the number of particles in the container remain the same. Okay, that remains the same. The only thing we're changing is the volume, the size of the container. So now these particles have more room to move around in. Okay, so you can see that those particles have more room to move around in. So how do you think that affects the pressure? So let's kind of write this out here. So the volume went up, right? Larger volume. So now we're trying to figure out how this affects the pressure. So do you think that the pressure is increasing or the pressure is decreasing? Do you think there will be more collisions or less collisions? So when you increase the volume, the pressure goes down. It will decrease the pressure because now they have more room to move around. They will create fewer collisions. Okay, therefore less pressure. Now what if we make the volume smaller? Notice how we're making the size of the container here very small. Now all of those particles are kind of jammed in there. Okay, they're all tightly packed in there. They can't move around a whole lot. So now in this picture, the volume goes down, right? And then the pressure is going to go up because that's going to create more collisions, therefore more pressure. So you can see here that one goes up, the other one goes down. All right? So this is what we call an inverse or an indirect relationship. All right? Inverse or indirect. So part A on the investigation worksheet, which once again involved Boyles Law, you should have found that it was the multiplication that gave you that constant value. Okay, the multiplication. So that's the one that you should have circled on that worksheet. And then also you should have drawn a graph that looked like that. And that's what an inverse or an indirect graph looks like. So you should be able to identify the relationship based on the graph. Okay, so an inverse relationship graph will curve down like this one here. And when we are looking at this equation here, the little ones, so the P1, V1 equals P2, V2, the ones and twos refer to before conditions. So these would be like the before conditions, and then these would be the after conditions. So for an example, they would give you pressure and volume values, and then they're going to change the volume, and then they would want you to calculate the pressure based on that change. And one last thing that I want to add here, there's a question. It's asking you what is constant. Okay, so this one is a pressure and volume relationship. So what variable is missing? So that would be temperature. All right, so then in this case, the temperature is held constant, and we're going to be changing pressure and volume. Now go ahead and read this and fill in the blanks using the word bank at the bottom. So you should pause it, fill in your blanks, and then replay the video to see if you got it right. All right, so let's see. As volume decreases, you have the same number of particles collide with sides of a smaller container. Therefore, the pressure, what's going to happen to the pressure? So volume decreases, so volume goes down. Therefore, pressure increases. If you half the volume, you double the pressure. This is an inverse relationship. So hopefully all of you were able to get that right. Now we're going to talk about Gay-Lussac's law. So Gay-Lussac's law was part B in the investigation, and this one is a temperature and pressure relationship. So it's asking you what variable was constant. So the variable that's constant here, well, which variable is missing from the equation? Volume. Okay, so volume is constant in this one. And then, so let's think about what's happening here. If you increase temperature, what do you think happens to the pressure? Well, if you increase temperature, that increases the kinetic energy. The particles are moving around a lot more, therefore more collisions. So if you have more collisions, that means more pressure, right? So let's write this out. So if temperature goes up, So hold on. So if temperature goes up, right, more kinetic energy, more collisions, therefore pressure also goes up, okay? So you see how these go in the same direction? So if they go in the same direction, is this a direct or an inverse relationship? So this would be a direct relationship. And a direct relationship graph looks like this, okay? You basically have this increasing slope here. This is a direct relationship. So as one goes up, the other one also goes up. So that's what your graph should have looked like for Part B on the investigation worksheet. Also for Part B on that investigation, you should have circled the division, all right? The division is the one that gave you the constant value. All right, so go ahead and read this. Fill in the blanks using the word bank at the bottom, and then you should pause the video, fill it in, and then press play when you're ready to check your answers. All right, so here we go. As temperature increases, particle velocity is faster, increasing collisions, therefore pressure increases. If we double the Kelvin temperature, we're going to double the pressure. This is a direct relationship. All right, hopefully you got those right. Now let's go on to our last relationship that we're going to talk about. Now we're going to talk about Charles's Law. Now Charles's Law was not part of the investigation worksheet, so this is going to be something new that we're going to discuss. All right, so this is a volume and temperature relationship. So in this case, what is held constant? Notice in the equation, we only have volume and temperature, so then what's missing? So now it's pressure, okay? The pressure is held constant. Just by looking at the equation and looking at the graph, you should be able to identify if the relationship is inverse or if it's direct, okay? So notice there's division, and you have this straight line for your graph, so therefore it is direct. All right, this is a direct relationship. So let's think about this. To describe this relationship of volume and temperature, think of a balloon. A balloon is the very best example that I can give you. So let's actually think of a hot air balloon. So if we increase the temperature, in a hot air balloon, so in other words, you're adding the fire. All right, you're adding the fire to the hot air balloon. What happens to the volume of the hot air balloon? The volume, you would notice, also goes up, right? It expands, okay? So you increase the temperature, more collisions, therefore the volume of the balloon is also going to increase. So this is also true if you are referring to like latex balloons. So if you have a latex balloon and you fill it up with helium or you fill it up with air and you go outside on a very, very hot summer day, it's going to expand in size. So sometimes you might notice that if you fill them up with too much air or too much helium, they could pop because it's going to expand in size. Or sometimes you've noticed if you have all these nice balloons, and then you go inside an air-conditioned room, and then you probably notice that they start to shrivel and get smaller, all right? Because if the temperature goes down, then the collisions decrease, therefore the volume on your balloons are also going to decrease. Okay, so read this, fill in the blanks with the word bank, that's at the bottom. Pause it, do it all by yourself, and then press play to check your answers. Okay, so as the temperature of the gas inside a balloon decreases, the particle velocity is slower, making fewer collisions, and the volume of a balloon, therefore, decreases. If you half the Kelvin temperature, you half the volume, and this is a direct relationship. Okay? All right, so let's go ahead and go on to the next concept. For this entire chapter, when you do your math problems, the temperature has to be in Kelvin. Okay, the temperature has to be in Kelvin when you are doing your math problems for this chapter. So to convert Celsius into Kelvin, what do you have to do? You have to add 273 to it. So let me explain to you why it has to be in Kelvin. When they were plotting the data for Charles's law, they noticed here, right here, that it started at point negative 273 degrees Celsius. And in order to be a true direct relationship, it actually has to go through point 0. Okay? So, if we just convert it over to the Kelvin scale, then it would go through point 0 and then therefore be classified as a true direct relationship. All right, so now what we're going to do is, to simplify things, we're going to combine all three of those laws together. Boyles Law, Charles's Law, Gay-Lussac's Law, we're going to combine them all together into one equation. So you don't have to have all those separate names memorized, and you don't have to have all three of those equations memorized either. You just have to know this one here. So this is called the combined gas law, which puts all three of them, combines them all together into one, equation. This is just another way that the combined gas law could be written. I really don't use this one too much because I think it confuses students, where it has like the T's are on opposite sides, whereas this one over here has all the 1's on one side and all the 2's on one side. Okay, so P1 V1 over T1 equals P2 V2 over T2. All right, so that equation needs to be memorized. Now, if something remains constant, you can just cross that out on both sides of the equation. So sometimes it'll tell you in the problem, like, volume is held constant, or it's not changing. Or if it doesn't mention that variable at all, you can just assume that it is constant and then cross it out on both sides. So if the volume is constant, then you would just cross out the V's on both sides, then it just ends up being P1 over T1 equals P2 over T2. Okay? So that's how we will use the combined gas law. Now we're going to go on to what is called the ideal gas law. So the ideal gas law is based on the kinetic theory if everything that was stated in that theory was correct. So the difference between this one and the combined gas law is that there are no 1's and 2's here. Okay, it only has one set of conditions. And the other thing that's different about this equation, it involves moles. Okay, it has moles in it. So let's go on to the next slide so you can see what the equation looks like. All right, so here's the equation, and you need to have this memorized. PV equals nRT. All right, PV equals nRT. So P is pressure, V is volume, T is temperature, N represents moles, and then R is the universal gas constant. So for R, you're always going to plug in this number, 8.31, and then these are all the units for R. Liters, kPa over moles, Kelvin. Okay? You don't have to have that number memorized. I will have that provided on the test for you. Okay? Now, because these are all the units here for R, you have to pay attention to the units in the rest of the equation. That's why pressure has to be in kilopascals so that it can cross out with the kPa here. Volume has to be in liters, once again, so that can cross out right there in the R value. Temperature, no matter what, in this entire chapter, all the math problems, the temperature has to be in Kelvin. All right, because you notice here also in the equation, there's Kelvin there. And then, yes, N, which represents moles, all right, that definitely has to be in moles. So if you are given grams, you know how to convert grams into moles by using your periodic table. So this is another equation that you have to know for your test, and we will practice using this equation a little bit later. All right, now Avogadro, he has a hypothesis. And according to Avogadro's hypothesis, he says that if there are equal volumes of gas at the same pressure and temperature, they will contain the same number of molecules. So, in other words, all the conditions have to be the same for all of the gases. Same temperature, same pressure, and same volume. So therefore, if all the conditions are the same, then they will contain the same number of molecules. So here's an example. At STP, so remember STP stands for standard temperature and pressure. All right, so let's review that because you'll need to know that to answer some of the questions on your homework. So standard temperature, remember, is 273 Kelvin, and standard pressure is 101.3 kilopascals, and that's what we will mostly be using for this chapter. All right, so at STP, how many molecules are in 22.4 liters of helium, and then how many molecules will be in 22.4 liters of hydrogen? So the conditions are the same. They both have the same temperature, the same pressure, and the volume is also the same. So therefore, they will contain the same number of molecules. Well, let's figure out how many molecules that would be. Well, 22.4 liters is equal to 1 mole, right? Well, how many particles are in 1 mole? 1 mole equals 6.02 times 10 to the 23rd molecules. So therefore, both the helium and the hydrogen will contain 6.02 times 10 to the 23rd molecules because all of the conditions are the same. Now, what if we have a mixture of gases? And this is where Dalton's Law of partial pressures comes into play. So according to Dalton's Law of partial pressures, each gas will exert its own pressure. Okay, so once again, according to Dalton, each gas will exert its own pressure. So in order to find the total pressure of the whole container, all you would do is add up each individual gas. Okay, so that's how they got this equation. So PT, which is total pressure, will equal the pressure of gas 1, the pressure of gas 2, the pressure of gas 3, so on and so on. So all you do is add up each individual gas's pressure, and then therefore you would find the total pressure of the system. So now let's look at this example. So here we have 3 different gases. We have a green one, we have a red one, and we have a blue one. So we're going to put all of those gases into one container, and now we want to find out what this total pressure is going to be. So we have to add up each individual gas. Add up the 200, the 500, and the 400, and then we will get our total. So go ahead and add that up, and then you get 1100 kilopascals, okay? So once again, notice that each individual gas, green, red, and blue, they exert their own pressure. So now when we add them all into one container to find the total pressure, all we do is add all of those up together. Okay? So that is how you do Dalton's Law of partial pressure. We are also going to do a lab involving Dalton's Law of partial pressure. So I will talk more about this kind of stuff later because we're going to do a lab on this. All right, this is the very last concept of Chapter 12, and this is Graham's Law of Diffusion. All right, Graham's Law of Diffusion. So what does diffuse mean? Okay, diffuse. Diffuse means to spread out. All right, to spread out. So we know that these gas particles are moving around randomly, rapidly. They're in constant motion, right? So they are going to diffuse. According to Graham's Law of Diffusion, the large molecules move slower than the small molecules, okay? So it's based on their size. And so to find their size, what you would do is add up their molar masses from the periodic table, okay? You would add up their molar masses from the periodic table. So let's think about this. Smaller ones, or the lighter ones, are going to move faster than the heavier ones. So that makes sense, right? The lighter ones are going to move faster than the heavier ones. Okay, so now I have an example. Let's think about this. Let's think about perfume. Okay? Perfume contains molecules, gas particles, right? Because you can smell them. So do you think perfumes and colognes are going to be made out of large molecules or small molecules? So let's think about it. Think of the purpose of a perfume or a cologne. All right? So if you think about this, your colognes or perfumes are going to be made out of large molecules. Okay, they will be made out of large molecules because the purpose of a perfume or a cologne is you want that smell to stay on your body as long as possible, right? So you smell good. You don't want it to diffuse off of your body too quickly. Otherwise, you're going to have to reapply your perfume or cologne quite often, right? So, perfumes and colognes will be made out of larger molecules because you want those to move slower, okay? So that the smell or the odor, this good smelling odor, will stay on your body for a longer period of time. And we are also going to be doing a lab on Graham's Law of Diffusion.